Hi, my name is Stephen Burns. I'm a senior geophysicist with Geometrics. We're an equipment manufacturer based out of San Jose, California, though we ship equipment worldwide and have a worldwide customer network that we support. And I'm in the magnetics department. I'm also in the seismic department. And today we're going to do some active MASW. This is multi-channel analysis of surface waves. And to do this, we're going to use our Atom Seismograph, specifically our Atom-1 Seismograph, our Atom-1C, which is the yellow box. And attached to this is a vertical 2 Hz phone. And we're going to be using 11 of these to create a 60-foot long survey line. So each one is spaced by 6 foot. And then on the end of each survey line, we'll be taking 3 shots. These shots will be 6 foot offset. So it's roughly 10% offset on each side of the line. 3 shots. And then after all this is done, I'll let these atoms collect passive seismic data for about 20 minutes. After that, it's pretty simple. Is download the data, put it on the laptop, process it, and we're going to walk through all that in this video. So if you want to see how to do some active MASW, and we're going to keep it very, very simple. If you want to watch that, watch this video. All right, see you on the other side. All right, I have all the atoms here. We have 11 of them. We're going to turn them on, and then I'm going to arrange them in order of serial number, so then I can put them in the line according to serial number going from lowest to highest. And we want to make sure all the atoms are on first before we arrange them. So we'll need the GPS light to be blinking rapidly. These are atoms with a button. So to turn each one on, you hold it for 3 seconds. So 1 1000, 2 1000, 3 1000. They'll turn on just like that. And we'll go through all these. 1, 2, 3. And the way you can check if an atom is on is to give it a tap test. So you simply just tap the geophone on the top and the lights will blink. So I might look at this one and say, hey, it's not on, or something like that, maybe 7. But if I move it around, I will see the lights all turn on. But 11 looks off. 11 doesn't look like it turned on. So I'll do this again. 1, 2, 3. And there we go. So they are all now connecting to GPS, and none of them have a GPS connection yet, so I'm going to line them up, all right? You can keep these unlined up. You could definitely have them distributed throughout your line, not according to serial number, but it's just way easier to do this and to turn them all on first. Make sure they all have a GPS lock. Again, when they're locked, the data is being collected, so you can just filter out that data, that maybe that 5 minutes, 10 minutes of data that's being collected before your actual survey start time that you put in your notes. You can just filter that out, but this makes sure you get really just very consistent surveys done. You want a methodology to follow. You don't want to be willy-nilly in the field doing something new each time. If you have consistent things that you follow through with every time, you'll have way less confounding variables that potentially throw off your data. And we're looking to get really good, high-quality data here, so that is always the objective. Most of the atoms are GPS locked now. They're all in order from 3 to 71. For this active MASW survey, I've set the 11 Atom-1Cs to a 1 millisecond sample rate. So this will make sure that we get a fast enough sample rate to collect the active data. That way when we do our off-end shots and we process it that way, the data is sufficiently sampled. Here I am laying out the atoms, making sure each geophone is coupled well into the ground. And these are again being laid out in order of serial number. So before you start, you should always do a final walk down your line. Make sure all your geophones are well coupled. Maybe someone else put them out, so make sure they're well coupled. They don't have any deviation on them. And also make sure all your atoms are collecting data, that the GPS light is blinking rapidly, and just everything is according to plan. There's no mistakes, because once you collect your data, there's no going back out to the field. Let me show you the last atom on this line. This is the 60-foot mark right here. You see that? And where we will be taking one of the shots, the end shots, is at 66 feet. So you can see 66 feet. And because these geophones are actually offset from their distance from that line, I'm gonna be taking the shot that same distance off of this measuring tape to right about here. So make sure when you're doing your off-end shots, you're doing them in line with the geophones, not necessarily the receivers. It depends on how you set everything up. So 3 hits, space them out by about 10 seconds. That way they're very clearly distinguished in the seismic record. And yeah, it's pretty simple. Just do a good hammer hit. After you collect your data on one end and do your off-end shot, go to the other side and do 3 shots there. So while we're waiting for the passive data, because now we're collecting passive data for 20 minutes, I'll show you just a little bit of the geology for the area. It's a little dirty, but this is shale. So we have some really good shale here, and this is very, very high velocity. It's very fast. So this will be interesting to see how it turns out. But on top of all this shale, we have pretty good clay. So there'll be definitely a 2-layer model here where we have clay and then where we have the shale. Just wanted to give a little bit of reference for when we're processing the data, why it's so high velocity. It's because of all this stuff that's around here. So we're in central Pennsylvania. It's beautiful outside. It's fall. It's absolutely amazing right now. And what a great time to do some active MASW. All right, so I collected all the atoms. I've turned them off with a simple button press of just 0 length. And now we're going to download the data. And I already have an Atom downloader video. So to see the actual software process of downloading the data, click that video up there. But in terms of actually downloading the data, you'll need a Wi-Fi access point. We sell ruggedized and non-ruggedized versions like this one. This is the non-ruggedized. And you'll need a cable to connect that Wi-Fi access point to your laptop. And you might need a driver to help these guys all speak together. So that will be linked in this video. But it's pretty simple. And the order of operations for downloading data off of your Atom is to first, of course, get your laptop on. But then you want to turn this on, connect it to your laptop, connect to the open network Atom-1C. Then you want to turn your atoms on. You don't want to turn your atoms on before you turn this on, or else they might not connect. But if you have this on first, they will definitely connect to it. Then lastly, you open up the Atom downloader app. Take your time slice of data, cut it, select it, and then download it to whatever folder you want. I'm not going to turn these on until this is fully turned on, but I will get it plugged in. So I will take a USB port, plug in the USB cable, find that input, get it plugged in, and set it up like that. Now the blue light is solid on the Wi-Fi access point, so I can begin turning on the atoms. So the way you turn on an atom is you just hold the button for 6 seconds. So for a count of 6, so 1, 2, 3, 4, 5, 6. And it'll beep twice, and that's how you know you're in data download mode. And you don't want these too close to your Wi-Fi point. You want them spread out just a little bit. So that way there's a little bit of a connection, a gap between the two. It just helps a wireless connection, I find. So we'll turn these all on. All right, they're all on. Our wireless access point is there. Now we just need to go to our Wi-Fi networks, and we'll see Atom-1C pop up. Connect to that. Do not click connect automatically. Just connect to it each time you want to connect to it. If you do connect automatically, it can just make things complicated. So avoid all those prompts. And you don't have to wait for it to say connected. You can just kind of exit out of that. It will be connected. And then you open up the Atom Downloader, and from there you basically just select your data. All the atoms will show up on the screen. If an atom doesn't show up in the Atom Downloader, or the access is bad, it's just not connecting well, then turn it off, turn it on. That usually fixes the problem. So I'm going to download this data, and then we're going to start processing data so you can see what the active MASW data looks like here in central Pennsylvania, and also what the passive MASW data looks like. All right, so now we're going to process our active MASW data. I've already done some processing on this so I could see what it looks like and the whole workflow. I've processed both passive and active data. But I'll be redoing this, and we'll be going through the whole process so you can see how you can use the Atom Seismograph to process active MASW data. So this right here is our active MASW data, and then this is some passive data I collected. I'll be explaining it all. But to start, you want to open up SPAC+. So this is a SeisImager module, and I already have it open here. We're going to go to File, Open Folder. We're going to go to Active Demo and click that folder there. Hit OK. It's going to load the files. And 11 seismographs have been found. One common time block. Here they all are. If I hit the up arrow, I'll increase the gain on the signal. And very quickly, you can see here the 3 hammer hits that I did. First on this side, and then also the 3 hammer hits I did on this side. So that right there is the active data that we will be processing. But remember, I also collected 20 minutes of passive data here. So I'll mention that in a moment. So if you want to select this data, you want to make sure you have that time block. Now, I already went and selected this data using the Atom Downloader. I sliced it exactly how I wanted it based off of values I wrote down in my notebook. So if you want to learn how to use the Atom Downloader, you can watch the video. But basically, we want to select this common time block here. And this is all our atoms from serial number 3 all the way down to serial number 71. Or maybe it's 72. And we'll hit common time block. I do not want to apply the bandpass. And let's increase the gain on this again so I see where I want to zoom in on my data. And for the active MASW, all this data here to the right of 300 seconds is not important. And the data here to the left of 100 also isn't important. So using the right arrow, I'll move my yellow gate to 100. And if you hold shift and use right arrow, it'll do a smaller jump. So right now it's shift and right arrow. Then I'll hit tab to go to the other gate on the other side, and I'll just hit just the left arrow to do some big jumps. And it's moving its way to 300. You can hit it pretty rapidly too. See that? And just a couple on the shift. Left arrow should do it. Okay, we have our window now. Now I can hit the clips right here, the scissors. So I'll hit clips, and look at that. There our data goes. I'll move myself out of the way a little bit so you can see. Those are our hammer hits, and I separated each by about 10 seconds. You can see that very clearly. So now we want to go to edit, and we want to go to event, shot detection, and then we want to go to detect event. So again, it's edit, event, shot detection, detect events. And we have a few options here. I basically leave the defaults. Then you have your time window 1 and your time window 2, and it looks at these two and creates a ratio in order to detect different events. Now the default that this is set to is 10. So we'll see what happens when I hit 10. And you'll see it said 27 events detected. Now it detected 1, 2, and 3. And it also detected 1, 2, and 3 over here, but it detected all these small little guys. This is actually me walking down the line to get to the other side, and this is me walking back. So clearly our ratio is too low, so let's increase that again. So we go to Edit, Event Shot Detection, Detect Events. 10 didn't work. Let's do 30. You hit OK. 7 events detected. Good, it only picked up this one here. And to get rid of that one, we can hit the arrow key, select it, and delete it. So now we have 6 events. 1, 2, 3, 4, 5, 6. And from each of these 6 events, we create a 2-second data file that we then analyze using PickWin. So PickWin is where you can do your active MASW analysis. So now we want to go to Edit and cut out shot records as SEG2 files based on detected events. So we'll click that and we'll save it as a 2-second file, hit OK. Receiver spacing was 6. Okay, 6 files are saved. And do we want to show shot records by PickWin? And we'll hit yes, and this will take us to PickWin. So PickWin is a SeisImager module that many are familiar with. And what it loads first off is it loads off your file list for your different shots. So basically each file and then your source locations, the receiver, and then the interval and all this. So the first hammer hits we did were at -6 feet. So we'll put in -6. And the next ones were at 66 feet on the line. And you know which one is which based off of this timestamp here. So 2020, 11/5. And then we have, you can see clearly here the time. And this is 29 and 41 and 53. Well, really it's 2 minutes, 29, 2:20, right? So you can see that it increases and there's a bit of a jump here. So this is how you're going to tell which event is which or which file is which. And then the first receiver was at 0 for all of them. The receiver interval was 6 for all these files because it was the same. And this is active data. You don't really need to mess with any of this stuff. Hit OK. So I can now increase the screen. I'm going to toggle this. It's a little easier to see. So blue down arrow will bring it and make it smaller. And then cyan left arrow will kind of taper it in a bit. And if I hit these yellow and red arrow keys, we can cycle through them. Up green arrow, it will increase your gain, and let's clip these traces using that. And then we can go through our files here. Now we're at the first shot, second shot, third shot, fourth shot, fifth shot, sixth shot. So all very clear there. And at this point, it's pretty simple. You go to surface wave analysis, phase velocity, frequency transformation. So again, it's surface wave analysis, phase velocity, frequency transformation. Click that. And you might need to play with these values a bit to find out exactly where you need them to end up. I know that this endpoint of 5,000 feet per second is pretty good, and this end range of 50 hertz is fine. So hit OK. And again, so we have some data, but I'm going to make it smaller so it's easier to see. So I need to really bring it in here. And here is our active MASW data. And remember, this is done over a fairly shallow clay layer, and then bedrock's pretty close to the surface, and this is a hard shale. So this isn't as pretty as I might like it, but definitely there's still data to look at here. I would say right off the bat, I see this nice layer here at around 1,000 feet per second, and at a frequency range of 30 to 25, maybe 23. So that could be our top layer of clay. And then we see a very nice kind of tornado here, right? Very nice bend there. And then up here, it's kind of unknown, but it doesn't look like we have good data beyond 15 hertz going to 0 with this active investigation. So really, we have data from 15 to maybe about 32 hertz. That's pretty clear. So to get the software to make its picks, which then we can move around, you'll click Pick Phase Velocities. So I'll click that. There's also an advanced menu here. So there's different things you can do here. You can put wavelength limitation on. You can turn that off. All these, you can set your minimum and maximum phase velocities. But for right now, this is fine. And we've already identified that this is probably the max. So I'm going to set that to 35. And well, maybe I'll just have to live with 50. We can deal with that a different way. So 5 to 50, it looks good. We'll hit OK. And here are the computer picks. So kind of all over the place, but again, we're just disregarding everything from 0 to 15. I do like this right here though. And of course, we'll be disregarding that too, disregarding this. So let's add a little bit to this layer here. And actually, let's just kind of create a straight line going like that right there. So a little exaggerated, but that's what it is. And then when I look at this, I do see a very nice region right here that's very constrained. So that's good. So we can draw a line through that. But then the question is, do you draw a line to here? Do you draw a line to there? Where do you draw a line to? And when I look at this, you definitely draw a line here, but I'd say the channel is more kind of in between. So you do see these points over here, and this one's a little close to the edge. I would say you're better off picking right in this channel in between. So I'm going to drag all the way from the bottom there. And I'm going to drag right through that channel. You can see what I'm doing. And I'll drag it to about 4,000. We have a good clumping of points here. We only have one that's beyond 4,000. So I'll drag it kind of in that channel, this blue channel, right, to about 4,000. And there we go. And I'll simply just draw a line going across here. We have some data there. That's the best we got. And I will say I've processed this data, and I know the passive data is much better for the lower frequency. So we'll actually be using the passive data there. But if I was to process this solely as MASW data, then I would draw a line there. So this is what I'd be left with. You have this layer here. You have the boundary zone, right, the transition from them, and then you have your next layer up here. This is your hard shale, this is your clay. So at this point, you have your picks, and of course you have all this junk here, but we can get rid of that. And the way we get rid of that is we go to Wave EQ. So you want to click on Surface Wave Analysis. You want to click on Show Phase Velocity Curve, launches Wave EQ. That's what we're going to do. We'll launch that. There's no coordinates. I'm just going to skip the coordinates for now. Doesn't matter. And if you only have your scale set to, let's say, 0 to 35, when you go and delete these points, you'll think you'll have deleted everything, but in reality you won't. You might need to set your view to something like 100. Because look, hey, there's more points over here. So the way you delete points is you go to this red box with the white arrow, you click that, and now you can just drag over these points and delete them. And you can drag any which way. It's just a left click drag. And I can reset my view again now. So I'll reset it to 35. There we are. And I can actually increase the scale a little bit. And that's our active MASW model. We'll hit VR for the apparent velocity model. And here it is. And I really like this data here. That transition was very clear. That funnel was very clear on the active data. Basically, what frequency range does that transition from a shale to clay happen at. It's basically 20 to 25. So what we can do is we can save this as an RST, and we'll save it before any iterations. Skip the coordinates, and I will save it to our active demo, and I'll call this the active MASW data. We'll hit save. Okay, great. So at this point, what we could do is we could hit the apparent velocity model, see that we have data to about 100 feet, which is what you need for a VS 100, which is the typical use for active MASW. So we'll click here, click initial model, and we'll put that at 105 feet, 10 layers. Again, there's an advanced menu. We'll just keep it simple today, and we'll hit OK. Here's our model, and I can actually change this configuration, so this is now 150 feet. And that'll look a little nicer. Okay, so now if I wanted to, I could also invert this, right? So this is our raw model, and if we go to dispersion curve here and click the red star, we'll get our theoretical, which is quite a bit off. This is definitely different geometry than, or different geology than normal. But if we go back to our VS model here, we can now invert this. Do 5 inversions. And it looks like our average shear wave velocity for the top 100 feet is 2,100 feet per second. This is before any iterations. And this can take a little bit of time. So we'll fast forward at this point. And here is our iterated model. And we have 2,248 feet per second as our average shear wave velocity for the top 100 feet. And if we go back to our theoretical, it's improved quite a bit. This actually might benefit from doing a second set of iterations. So we'll invert it 5 more times. And we'll fast forward through this too. All right, that's finished. Roughly the same here. And if you go to display, calculate theoretical, now it's quite a bit better. It's 340. I could probably iterate it again and improve that a bit more. But overall, at this point, I think this is fairly good. And I typically don't like to iterate data too much. So we'll leave it as is. This is a tough site. This is, again, very shallow clay layer over very fast, very high velocity shale. So that's our model from just doing the active MASW. That's how you process. You start off with SBAC+. You detect your events. Then you go through, save your records, process it in Pickwin, and move over to WaveEQ. But there's more to the story than just the active MASW. We also collected passive data. So first off, we collected passive data with the linear line that I set up, that 60-foot line of 11 atoms. And let me show you what that data looked like. I'll move myself onto the coherencies here. And if we look here, we'll see that this is our passive data from the linear line of 60 feet. And we have this layer here, which roughly is about the same as the active data, going from 20 to 30 hertz. So we have that, and then we also have much better low frequency data from the passive. And there's definitely a trend here, though it's pretty broad. I mean, it goes from 4,300 all the way to 2,900, all just right there at 6 hertz. So this is pretty broad, and there's also no real connection point there. But remember, we had a good connection point on the active data. That was really nice and clear. So When I saw this though, I know that the linear arrays don't work the best for passive. They're definitely not as good, especially at low frequency response. So I went out and I did another passive survey, and this time it was a 60-foot half circle. So this was 60 feet and 30 feet up, so 30-foot radius, and that created some really good spacings and pairings going in between the circle, while at the same time sticking to the parameters of this survey, which was being 60 feet in length. So I didn't want it to, for the purpose of this, I didn't want to change the parameters. I wanted to stay at a 60-foot total length and with 11 atoms. So I did that, but it goes to show you the power of survey design, because this is our linear, and if I click over, this is our semicircle. So if you look on the right side, how noisy the data is, and then it definitely cleans up with the half circle array. And also our clay layer also improves. If we go here, that definitely looks better. So we have data, but fairly noisy, and then we have pretty good data. I'm pretty confident in that. That looks pretty good. So we'll process with this, and we will use the active section. That tornado up on the active was really good. We'll use that, and we'll combine it with this passive data for our final result. So let's process the passive data. We're going to process that half circle passive data. So I'll close out of this, and you'll want to go to SPAC+. And what we'll do is we'll exit out of Pickwin. We'll exit out of, because we already saved this. Let's confirm. Active MASW, yep. So we'll exit out of WaveEQ. And now, again, we have our data here. And normally we process with this half of it. So you do your active data collection, and then you leave it out for 20 minutes, collect passive data, process those two together. But I already noticed how the passive data, I went out and collected a better passive data set. So we're going to use that. Maybe normally you wouldn't do that. You would just have your line set out. But the whole point of this is to illustrate that there's better survey geometries than lines. So we'll hit X there, open, new, open folder, and we'll click passive 2. And this data was also collected for longer. So it was collected for 40 minutes rather than 20 minutes, which makes a difference. Even though it's a small array, it's only 60 feet, extra time definitely helps clean up the data. So 11 seismographs, okay. 1 common time block. And here I didn't do any active work, so I can just go straight to common time block. And no bandpass. Our data looks good. If I move myself down, you can see there's really nothing to be concerned about. Maybe a little bit of something here. Who knows what that's from, but might remove it. And if I hit SPAC, then I can put in my geometry. So I already created the geometry file, and basically to get there, I need to go here, and I'll click array 11. And this is the half circle geometry array. So we'll hit open, okay, and then okay. So now it's going to show us that we have 11 receivers, the number of time blocks we have, and I think I have it set to 20 seconds because we collected data for 40 minutes. So that'd be about right, something around there. 15 seconds. So hit OK. And then we have 55 pairs, 23 spacings. So better than the line. Not the normal mass spacings I like, but it's good data. Hit OK. And we'll see this pop up. It's crunching numbers. Okay, so I'm going to hit up arrow so I can increase the raw data gain a little bit. I want to remove those blips here. Just whatever that is, I don't know what it is, so I want to remove it. So I'm going to click it, hit delete, click the other one. It's the wrong one. Click that one. Hit delete. And the way passive seismic works, this method, the SPAC plus method, is that it works off of averages. So averages, each one of these time blocks is one of these lines here, and it creates, does a Fourier transform on the data, and it creates basically these coherency plots. And I'm not going to get into it too much because this is an active MASW video, but basically it creates averages. So me removing these two blocks there is not a big deal because look at how many blocks we still have left. And honestly, I could have left them in, probably would have made no difference. But if I see something like that, I typically remove it. And we'll just scroll through these coherencies. The higher the coherency, the better. So a coherency of 1 means that it's the data is exactly similar coming in across these receivers at different wavelengths. And then a coherency of 0 means there's no similarity. And a coherency of -1 means that there is opposite similarity. So really good coherencies all the way up, all the way through 10. Then they start to go down below 10. And that's where the active data really does better. Active data does better in that 10 to 30 hertz range, 10 to 30, 10 to 40, maybe 50. So the passive data you can see is really good coherency, especially at these longer wavelengths I just scrolled to. Here's 60. We still have really good coherency at some of these higher, these lower frequencies, so these longer wavelengths. So there's clearly a good low frequency response here. A dip at 1, that's fairly common. Still trying to figure out exactly why that is. It might be due to water and hydrological processes. But we'll go to our phase velocity dispersion curve now. We'll hit OK at minimum frequency be shown is 30. That sounds fine. I'll move myself back over to the coherencies. But we do see the coherencies at all our different distances. They all look good because they're all in the positive, right? So overall, good data here. And I'm just going to, normally I would pick through this, but I'm just going to export this as it is, and then we can smooth out this data. So yeah, I think that's best because I'm going to combine this with the active data, and that will help us see what we need to get rid of, what we don't need to get rid of. So at this point, I'm just going to go straight to this. This launches wave EQ and launches the dispersion curve. And I will do some cleanup here. Namely, I'll clean that. I'll clean that. And I'll also will get rid of all this stuff below here and just we'll use this to start. So now we can go open, file open, and we'll open up our active MASW file. Well, actually, let me save this first. So I'll go here, I'll save this first just in case, and we'll call this passive. And we'll save it. And now I'll open up the active, and it'll say new data or append. So new data will just completely replace what's on your screen with the data that you're opening. Append will add it to the data, and whether you want them to just become one data set or two depends on you. If you average the same frequency, it becomes one data set. If you don't, then they go in as two different files that you can average later if you wanted to. So we'll hit no. And here we can see our active data, and we can see there's rough similarities between them. I'm going to keep, we know that the active does better for the higher frequencies, so I like this layer here much more. If we look at our data, this is, I like that zone more than I do this. They're fairly similar, but there is a difference between them. So I I just like that more. It's very well constrained. So we're going to keep that with the active, which means that when it comes to this passive data here, I'm going to delete those. I'm going to delete, I got to be careful when I delete these. I'll just leave some of those red ones there. And at this point, the active had that line, but if we go back to our graph or our phase velocity, I mean, this is really pretty arbitrary, right? And this is much better. This is much better. So, and you can see again the difference between the line and the half circle. But we're going to go off of this. So I will delete the active data for up here. I'll delete those two, but I do like overall this. This is implying a low velocity zone, which is a little odd. So we have to be careful with how we process this. Before we do anything too drastic, let's look at the parent velocity model. And we can see right off the bat that we can get rid of those, we can get rid of those. Looks like I missed a point. Let's increase this to 300. So we have data going all the way throughout. And maybe this is a hydrologic layer right there. Maybe we have groundwater at 50, right? That could explain that 1 Hertz dip. So that could be the reason why, but overall this looks pretty good. It's broad, going from 3,000 to 3,500, but it's well constrained in there. So let's get rid of those, look at, and then go back to this. So we'll go here, we'll click our red box with the arrow, and we'll delete those, and we'll delete these, and then there was that guy. We'll go back to VR. All right. And what you could do, because this was collected right by a creek, so I bet groundwater's at 50. So maybe we can. It's probably too late to draw a line going from here to there, but if you go display, let's do some smoothing. So that's what our smoothing did. And it creates that nice dip there. Well, what would we have? Data to 250. Let's see what our initial model looks like. Here's our initial model. Let's not manipulate this data too much. Let's leave it as it is. I do like this. I like that active component, and then the passive data that's the passive data we collected. We did a little smoothing on it. And if you go back here, what I could do is I could cut through some of these guys and basically cut the tops and bottoms off and do a little bit of smoothing that way. Because when you re-smooth, it'll create new dots in between. So we'll just do a little bit of that, not too much. But that should make this data a little easier. To kind of read and to understand. A couple more of these guys. And what we'll do now is we'll do that smoothing again. And this time it didn't go in between. No matter. So we can go back to our velocity model here. We'll click that up. And we've already created our initial model. Now we want to do inversion. And we saw with the active that we had to invert it about 10 times. If we click the red star at our dispersion curve, we'll see that our RMSE is 500. So let's just do 5 to start, see what happens. I'm going to speed forward through this. Okay, so it's done inverting, and that's our model. A little wacky, but could be reality. And we'll hit the red star for our theoretical, and it's definitely improved. It's tightened up on this, diverged from that, but then it kind of gets closer again to it. So 371, and let's do one more inversion, another 5 rounds, hit OK. We'll fast forward through this. Okay, so the iteration is completed, and if we look, we'll hit the curve again, and it's definitely better now. So it's at 328, just by a little bit. And final model is not as clean as I would like. I wish this low velocity zone wasn't there. We could always just delete that, right, and just go straight from there to here. But I really think that active portion was pretty clear. Let's go back to that. That active portion going from 800 or so all the way to about 3,000, 3,500. It's pretty clear. It's a pretty clear channel. And that portion, the low velocity portion, starts at 2,500. So 2,500 would be here. So if we cut across and did our increase from there, so it'd be something like this, going here and then. So there's a lot of ways. Every site's unique, and you have to do a lot of surveys to really be able to know what to how to process this data. But this is a unique site because it's very, very shallow, very, very small clay layer, and then it's a very thick and high velocity shale layer. And these areas are known for having higher modes. So this could be the higher mode potentially, right? This could be a higher mode, and maybe the data actually goes like this, it goes down. We also have a very good low frequency response for this survey, even though we only got data, we only had 60 feet of data. So there's a lot of ways to interpret this. I'm not going to go any further than this, and that's because we don't have any actual survey on the line here. But that active data, if you want to look at the data again, we have our active data here, right? And maybe I can layer this with the passive data. And actually that's the one I wanted, okay. I'll move myself kind of up here. And you can, of course, they're flipped, so they are different, but that is the active MASW, and this is the passive, and you can see how they can be used together in these sites that have geology that is a little more difficult to do MASW with. That's why typically a lot of people do refraction here, right? Very simple to get depth of bedrock with a site like this. But we are doing surface wave analysis. So it's a little bit of a different game, a little bit of a different ball game. Thank you all for watching, and I hope that you appreciate this video and the processing steps of how to process active MASW using Atom seismographs. And then we went further down the rabbit hole and looked at the passive too. So if you made it here, very cool. If you have any questions, you can always email seismicsales@geometrics.com. We'd be happy to help you either with Atom inquiries and getting a quote, or for SeisImager getting a quote, or for general help like this in understanding the software, how to process the data, things of that nature. So we're always happy to help you out. And until next time, ciao.